Phase diagram. Phase is a homogeneous part of a system in contact with other parts of the system but separated from well-defined boundary. Phase can consist of solid, liquid, or gas. These are the example of three-phase system. Here is water vapor, gas form, salt plus water, aqueous, and this is salt, solid. So three phases we can differentiate. This is gas, aqueous solution, and solid form. Example, a cup of coffee, one phase, liquid, because you cannot differentiate the coffee from the water. So it's a solution of coffee, one phase. This one, oil plus water, two phases, because you can differentiate which one is oil, which one is water. Both are liquids, but you can differentiate them, so it's two phases. This one, mixture of gases. We cannot differentiate which type of gases or one by one, so this is one phase. It's in gas form. Mixture of gases, one phase. Gases are well mixed. We cannot see the boundary between the gases. You cannot differentiate the gases. Two liquids, do not mix oil and water, two phases, because we can see the difference between oil and water. Two liquids well mixed, for example, alcohol and water, one phase, because you cannot differentiate which one is alcohol, which one is water, so one phase only. We cannot see the boundary of the solution. Phase diagram, a diagram showing the regions of pressure and temperature, pressure on the y-axis, temperature on the x-axis. So this diagram shows the region which a substance exists as solid, liquid, or vapor or gas. Phases are thermodynamically stable. So this line is the boundary between, for example, from O to A, boundary between liquid and gas, from O to C, boundary between solid and liquid, boundary from B to O, the boundary of solid and gas. So this is the phase diagram. This one, line OA, liquid to gas. This line, any point of this line, the substance exists as liquid and gas. It's a boundary between liquid and gas, so any point here liquid, any point here gas. On the OA, it can exist as liquid and gas. And OC, solid liquid, OB, solid gas. So from A to B, here we know that this is solid, liquid, and gas region. Solid region, liquid region, gas region. So from A to B means from gas to solid. So gas here, and then on the line, gas and solid, and any point above this line in this region to B is in solid form. From B to C, here any point in this region in solid form, and on the line B to C, on the line it's liquid and solid, mixture of liquid and solid, and after this line to C it's liquid form, and from C to D, before this line, from C to D before this line it's liquid form, on the line liquid gas, and after this line to D it's in gas form. From D to E, same, gas to liquid. So from gas to liquid on the line, mixture of gas liquid. And then from EF liquid to solid form. So here, any point here, it's in the liquid form, and on the line, liquid solid, and after the line to F, it's in solid form. FG, F solid till on the line, solid liquid. After this line to G, it's in liquid form. So this is a phase diagram. This is how you differentiate at which point what phase is the substance is. Triple point. Here is the triple point. The mid of this line, OC, OA and OB. The meeting point of OC, OA and OB is the triple point. Here, solid, liquid and gas or vapor simultaneously exist in equilibrium. So here, 3 state of matter can be formed: solid, liquid and gas at the triple point. So point 1 on the line, so we know that A is solid, B liquid, C gas. So point 1 on the line, A and C, solid and gas. Point 2 here, this is at the triple point. At the triple point, solid, liquid and gas exist here. Point number 3, on the line of boundary between C and B, B is liquid, C is gas. So on the line of the boundary between B and C, there are liquid and gas form. Point number 5, here, boundary between solid and liquid. So on the line, there are solid and liquid form. Critical point here, triple point. Here is the critical point. Critical point is at the end of liquid gas line. So here, liquid gas line, the boundary between liquid and vapor or liquid and gas. So at the end here, we call it critical point. It is the highest temperature, so temperature on the x-axis, highest temperature at which gas can be liquefied. So here, highest temperature, gas can form liquid. Density of liquid is equal to the density of the gas at the critical point. Above critical point, the liquid phase cannot exist anymore, no matter how low or how high the pressure is. So after this point, there is no liquid form anymore, only gas form. Phase boundaries disappears. So after this point, phase boundaries disappear. Separation of liquid and gas phase no longer exists after this point. At this point, the average kinetic energy of the molecules is so high that the vapor cannot be condensed no matter how much pressure is applied. So here, after here, the average kinetic energy is so high that the vapor cannot be condensed or the vapor cannot be liquid anymore, no matter how much pressure you apply. Example of phase diagram for carbon dioxide. So for carbon dioxide, at 1 atm, here, negative 78 degrees Celsius, 1 atm, carbon dioxide can be found as solid and gas at 1 atm at negative 78 degrees Celsius. Carbon dioxide is a gas under normal conditions. So here, at 25 degrees Celsius at 1 atm, carbon dioxide is gas. But at 1 atm negative 78 degrees Celsius, carbon dioxide can be formed or can be found as solid and gas. Here at negative 57 degrees Celsius at 5.2 atm, carbon dioxide can be found as solid, liquid, and also gas. So line OA line, carbon dioxide, solid and gas. So on this line, carbon dioxide, solid and gas can be found on this line. Solid and gas exist in equilibrium. OB, boundary between solid and liquid. At OB line, carbon dioxide can be formed in solid and liquid form. So here, this line is the melting or freezing line. At OC, the boundary between liquid and gas or liquid or vapor, carbon dioxide can be formed in the form as liquid and gas, any point on this line. Liquid and gas exist in equilibrium. Point O, here, triple point. Triple point at negative 57 degrees Celsius at 5.2 atmospheric pressure, carbon dioxide can be formed as solid, liquid, and gas. Solid, liquid, and gas or vapor exist in equilibrium at the triple point, at point O. Here, critical point. Above the critical point, the liquid phase cannot exist anymore. This is the highest point where liquid and gas can be found for carbon dioxide. Above this point, liquid cannot exist anymore regardless of pressure. It is at the temperature of 31 degrees Celsius and at the pressure of 73 atmospheric pressure. That's the critical point for carbon dioxide. At pressure below 5.2 atmospheric pressure, any region, anywhere below 5.2 atmospheric pressure, phase change from solid to gas, or can change from gas to solid but not liquid, because for liquid it needs to be more than 5.2 atmospheric pressure. So when solid carbon dioxide heated at 1 atm, it sublimes at negative 78 degrees Celsius. At pressure above 5.2 atm, you can find carbon dioxide in gas, liquid, and solid form. If the temperature is high, above 5.2, you can find it in gas form. Any temperature here, slightly above negative 57, you can find carbon dioxide as liquid form above 5.2. And here below negative 57, you can find carbon dioxide in solid form above 5.2 atmospheric pressure. At the temperature below negative 57 degrees Celsius, here, any region here, you can find carbon dioxide in solid or gas form. So it depends on the pressure. If the pressure is high, above 1, here, any region here, any region here, you can find carbon dioxide in solid form. And any region here, you can find carbon dioxide in gas form or vapor. And above negative 57 degrees Celsius, any point here, any point, any atmospheric pressure here, you can find the carbon dioxide in solid form, here liquid form, and any point here you can find carbon dioxide in gas form. The phase diagram for carbon dioxide is typical of most substances. If you see this line, solid liquid boundary line, is slightly tilted to the right. So you can say that this is the positive slope. If you see the phase diagram of any substance with positive slope, it means the melting point or freezing point, because we know that this line means a melting or freezing point. It means the melting or freezing point increase when the pressure increase. When you increase the pressure, the melting point and freezing point also increase. This is for carbon dioxide and for most substance with positive slope. Melting point increase when pressure increase because solid carbon dioxide is more dense than liquid carbon dioxide, means solid carbon dioxide occupies smaller volume than liquid carbon dioxide. At high pressure, it favors the formation of solid carbon dioxide, which has smaller volume. More heat is needed to melt the solid carbon dioxide. Solid carbon dioxide melts at high pressure and high temperature. Next, phase diagram for water. This is a phase diagram for water. You have solid, liquid, and vapor region. Water is a liquid under normal conditions. So we know that normal condition is 25 degrees Celsius and 1 atmospheric pressure. Here, normal condition. At 1 atmospheric pressure, here, if you see from left to right, when the temperature increase, the phase will change from solid to liquid to gas at 1 atmospheric pressure when you increase the temperature. And at 1 atmospheric pressure, melting or freezing point, we know melting or freezing point is the line between solid and liquid. It's at 0 degrees Celsius, and here, liquid and gas line, liquid and vapor line. Here, the boiling point. Boiling point is at 100 degrees Celsius for water. Point O, the triple point, water can exist. Here, water can exist as solid, can exist as liquid, it can also exist as gas at the triple point. If you want to have 3 types of matter, solid, liquid, and vapor, the pressure must be 0.006 atmospheric pressure and temperature must be 0.01 degrees Celsius. This is where you can find water in solid, liquid, and gas form. C. At critical point, the critical point is 374 degrees Celsius at 218 atmospheric pressure. After this point, you will only see water vapor in gas form. You cannot see the water in liquid form anymore after this critical point, no matter how much pressure you put. The phase diagram for water is one of few substances in solid liquid line slope. If you look at this slope, it's different from carbon dioxide. Carbon dioxide has positive slope. The slope is slightly tilted to the right for carbon dioxide. But for water, this slope is tilted to the left. Means it's negative slope. Negative slope means here if you increase the pressure, the temperature decrease. It means melting point decrease when the pressure increase. When increase the pressure, the melting point will decrease. Phase diagram of carbon dioxide and water. So this phase diagram is for carbon dioxide on the left. On the right is the phase diagram of water. The phase diagram for carbon dioxide has solid liquid curve. Here, positive slope. Carbon dioxide positive slope because it's tilted on to the right. And for water, solid liquid line with negative slope, slightly tilted to the left. So negative slope for water, positive slope for carbon dioxide. If solid is more dense than liquid, solid more dense than liquid, that's for carbon dioxide, the solid liquid line slope to the right. For water, solid is less dense than liquid. We know that ice is less dense than water. If the solid form is less dense than water, the slope will be negative. If solid is more dense than liquid, it will be positive slope. That's how you identify whether the slope is positive or negative. It depends on solid and liquid, which one is more denser. Thank you.